Okay, so now that we've talked about multi-step synthesis and about various reactions within the world of alkynes and a review of reactions of alkenes in a way, let's take a look at an example that looks like this one that's very common that you'll see on a test or a quiz or with any organic text. And this is the reaction wheel diagram of an alkyne. So in the center of this reaction wheel, you will see the alkyne listed. And this is just a general alkyne. Notice that they put an R here that means random alkyl group, whatever it wants to be. And we want to know what type of reagents would be required in order to get to these products that are listed on the spokes of the wheel. And then we're going to start with the first one up here on the left first. So we need to question ourselves, how can we go from an alkyne down to really an alkene? And that's what this guy is here, or alkane, sorry. And this is the removal of the triple bond and it's the removal of the double bond. So what type of reagents can we do? Well, here is H2 and platinum. If I used H2 and Linlar, it would stop it at a double bond. H2 and platinum, however, would take my triple down to a double and then immediately convert my double down to a single. And that's the only way that we know at this point to get an alkane as the ending product. So the very first one, how do I get this molecule? I'll add H2 and platinum in order to get it done. If I take a look at number 2, this is RCH double bond CH2. Well, I'm starting off with a triple bond and I'm ending with a double bond. So the only thing that I've done here is added hydrogen onto each side. There's no other functional groups that are listed there. I've added hydrogen on one side and hydrogen on the other. So I know that I'm going to have to add H2 to the system, but I've got to be careful because this is where Linlar will come into place. So H2 and Linlar would allow this triple bond alkyne to be converted to an alkene, which is what this molecule is. Notice there's no stereochemistry involved here. So that means I don't need to worry about H2 and Linlar or the sodium lithium example because no stereochemistry is shown. If no stereochemistry is shown, then you forget about it. So H2 and Linlar would be an acceptable answer to get to this point. One of the reasons that stereochemistry is not inserted in this example is because this ending carbon has two hydrogens, and you can't really compare a carbon to another carbon if one of those has two of the same groups on it, and this carbon has two hydrogens on it. Now let's take a look at example number 3, and this is converting the alkyne. And if I look, I get no single bond and no double bond at all. It's all single bonds throughout the molecule. But I've got a bromine here and a bromine there. So I've got to figure out, well, how on earth can I get two bromines onto the molecule and end up with single bonds all the way through the board? Well, if I add HBr to this molecule, H would go here on the end and play with other H's, and my bromo group would go here to the left. And that's what we want. H goes to the right and bromo goes to the left. But one round of HBr would only do this once. So I need 2 moles of HBr. So I would write 2 moles, or I would write the word excess here to make sure that I understand that this needs to happen all over again. So 1 round of HBr, H goes on one side, Br goes to the left. 2 rounds of HBr, H goes on to the right again, and bromo goes to the left again. So 2 moles or excess HBr would allow that to happen. If I come down here at the bottom at number 4, this is a double bond with a bromo hanging off of it. So this is very similar to the one from number 3. I would add HBr to this alkyne, and H comes to the right and Br goes to the left, but I only need 1 mole of it this time around. So H comes to the right, Br goes to the left, and now we get this alkene with the bromo group hanging off. So that's the answer for number 4. Now if I come around and just do number 5 here, and we'll just work ourselves on around, I've got to look at this functional group and realize that this is a aldehyde. And we know that aldehydes come from enols, and enols come from OH groups. So we need to add an OH group onto this molecule. But in order for the OH to be added on, I also need a double bond on that molecule as well. That's what enol means. En is double bond and all is OH. So what kind of reagent can I use in order to get this accomplished? Well, I need the OH group at the end. That's how the aldehydes get there. So BH3 THF with my onslaught of hydroxides, H2O2, H2O, and OH, would allow this triple bond to be broken to a double, and OH would go on the end. And that ending OH group would rearrange with the double bond to give me the aldehyde. So this is the general setup to convert the alkyne to an aldehyde. Okay, well, what about number 6? Number 6 is very similar, but it's a ketone, not an aldehyde this time around. The aldehydes, the double bond O is at the end, and the ketones, the double bond O is in the middle. So with the ketones, it's kind of the same thing. I need an enol here, and that enol requires an OH and a double bond. So I need some way to add on water. And I could, if I wanted, put water and maybe some acid here, sulfuric in a way. And this would put H onto the right and OH onto the left. And this OH and double bond would rearrange because that would form an enol, and that would give me a ketone. If I take a look at number 7, this is a bromo group, but it's single bonds. It's carbon, single bond, carbon. So this is going to require maybe 2 steps here, and I'm just going to kind of write the answer out here at number 7. And the very first thing that I probably would want to do would be to add H2 and Linlar for me. And the H2 and Linlar would take the triple bond and break it to a double bond. And then, once that double bond is formed, I can add HBr onto that molecule. And Br would go to the left, H would go to the right, and my double bond would break to a single. So H2 Linlar and HBr needs 2 sets of reagents here in order to get that accomplished. And then finally, number 8 is this whole epoxide containing group again. So what can we actually add to this alkyne to make this an epoxide? Well, again, this is probably going to take more than 1 step. So I can add H2 and Linlar first, and this will take my triple bond down to a double, and now we can work within the alkene family. Once the H2 and Linlar is added on and I have my alkene, I can then add my peroxy acid. And that peroxy acid in the previous video was C double bond O COOH. And this was the peroxy acid that allowed the epoxide formation to take place. So this is a reaction wheel. Expect to see one of these on the test. I've left out, this example has left out maybe some extras that I could have done. So we could have seen R, and we could have seen C, and we could have had a bromo here, and a bromo there, and a bromo here, and a bromo there. And what kind of general reagents would I need to see 4 bromos onto the molecule? So here we would use Br2 and DCM, and when we do that, this Br2 and DCM would need excess, because 1 round would put a bromo here and a bromo here. 2 rounds would put another bromo on that carbon and another bromo on that carbon. So Br2, DCM, and a little bit of excess to go on to get 4 bromos onto the carbon-containing group. So this is just an example of what you would see. It sums everything up quite nicely into one wheel diagram. So take a look at this problem and just be comfortable with bringing these reagents in to get what you need as far as the organics go.